You're here because you want to master the electrochemical cell or simple cells with a University of Cambridge graduate. This is actually part 1 of our electrochemistry series. If you would like to watch the next part after watching this lecture, do check out our playlist below so that you can watch the next video. Hi, I'm Brendan and I'm a University of Cambridge graduate who has been teaching chemistry to many students like you over the past 9 years. I'm also the founder of the Chemistry Institution, where we have helped many students improve in a short amount of time and achieve the grades of their dreams. Be sure to check out our website in the link in the description below so that you can download a free copy of the notes for yourself and use it to run through this lecture with me today. Electrochemistry as a whole is a very challenging chapter in Sec 4 that you have to master in order to do well for your O-levels or your secondary school. The concepts here are quite new and quite complex, so do pay attention to this. In this diagram over here, you can see a electrochemical cell, or you can call this a simple cell. What this means is we're actually using the power of chemical reactions to power and generate electricity. This electricity that we are generating is called a potential difference between the two half cells, the left and the right half cell. And this is actually measured via this voltmeter over here. The voltmeter is connected by wires to the electrodes, which are these rectangular rods over here that can conduct electricity. These rods or electrodes are dipped into these two beakers of solutions which are called the half cells. These solutions are also called the electrolyte. So for example, this zinc sulfate solution or this copper 2 nitrate solution are called electrolytes. Furthermore, to complete the circuit, these electrolytes are also connected via this thing called a salt bridge. The purpose of this salt bridge is to prevent mixing of both solutions in both half cells, but still let the ions pass through. And the salt bridge actually plays an important role because it's meant to keep your solutions electrically neutral so that there's no buildup of charges which could lead to the reactions stopping. In an electrochemical cell, typically we see each half cell have a specific metal, for example zinc, as the electrode, and the ion of that metal, which is zinc 2 plus over here on the right, inside the electrolyte. You can see it very similar in the left half cell as well, where copper is the metal, which is the electrode, and the copper 2 plus ion is also the electrolyte. What we're doing is actually capitalizing on the potential difference between both chemical reactions. The potential difference, or the reading on the voltmeter, actually will be determined by the difference in reactivity between these two metals. So if you refer to our reactivity series chapter, we know that zinc is actually more reactive than copper. And because of that, zinc will most likely undergo oxidation. So zinc would be oxidized to zinc 2 plus in this whole electrochemical cell, whereas on the other side, you will have reduction. And your copper 2 plus ions are going to be reduced to copper metal. In terms of observations, you will see that the electrode on the right half cell, which is the zinc half cell, would be shrinking because the zinc electrode is oxidizing. Now compare that to the left half cell, the copper electrode is actually going to be increasing in size because the copper 2 plus ions are reducing, and thus it will form deposits over this electrode. Once we have figured out which half cell has reduction and which half cell has oxidation, we can then tell which side is the cathode and which side is the anode. Since reduction happens on the left half cell, we can tell that this is actually the cathode. And we memorize this via this acronym called RED CAT, which stands for reduction happens at the cathode. On the right half cell, since oxidation happened, then we can tell that it is the anode. And we memorize this via this acronym called NOx, which stands for anode has oxidation. So I want you to take note that the further apart in reactivity between these two metals in these two half cells would create a larger potential difference and thus a larger voltmeter reading. Now let's run through step by step as to how to determine reactions at each of these electrodes. Number one, you want to identify the more reactive metal electrode. And again, you have to refer to your reactivity series, which you should have memorized from the reactivity series chapter. It is very important for electrochemistry as well. The more reactive metal's electrons will then flow to the less reactive metal. And with that said, you can identify which half cell has oxidation, which half cell has reduction, and furthermore, you can identify which is the anode and which is the cathode. This is very important for this chapter. Next, you want to identify the ions in the electrolyte and see which ions will go to each electrode. Typically, if you memorize your reactivity series, the ease of discharge table that you can see is actually the reactivity series, but it goes the opposite direction. So you can see that the more reactive metals actually have a harder time to be discharged. So if you memorize your reactivity series already, you don't really need to memorize this electrochemical series as well. Next, once you have identified which ions go to which electrode, you can then write the half equations at each of these electrodes. Remember, the goal is for the ion to become neutral, usually in a discharging reaction. So at the anode is where oxidation occurs and there is a loss of electrons. At the cathode is where reduction happens and there is a gain of electrons. So let's run through an example of an interpretation of the electrochemical cell. A typical question in the exam would just give you a cell like this and you have to find out what kind of reactions are happening. Let's say you have two electrodes, but this time they're both in the same electrolyte. So you don't really need a salt bridge here because the electrical current can just go in a whole circuit. Next, we have a copper electrode and a silver electrode, and it's in this silver nitrate electrolyte. In this particular instance, again, remember our first step is to identify the more reactive metal. Now, if you compare copper to silver, you should be able to tell, if you memorize the reactivity series, that copper is more reactive than silver. So in this step 1, you can already tell, since copper is more reactive, most likely oxidation would happen here. And if oxidation happens here, then the other side would have reduction. And remember our acronym, NOx. So we know that the anode is on the left side because that's where oxidation happened, and the cathode is on the right side because of the acronym red cat. Once we have identified which is the cathode and which is the anode, we now next need to identify the ions in the solution. So these ions are silver plus ion, NO3 minus ions, and because it's an aqueous solution, there's going to be water inside. So part of water is that there's going to be H plus and there's going to be OH minus inside this electrolyte. And because we know this, we can then sort them out and push the ions to their respective electrodes. So the cathode is going to attract the cations. So your H plus and silver plus ions are going to the right, and your NO3 minus and your OH minus is going to go to the left. Next, you can then write the half equations over here. So your cathode is going to have reduction that happens, and for this we want to look at the ease of discharge table. So if you refer to the ease of discharge table or the reactivity series, we can tell that if you compare H plus and silver plus actually is having an easier time to discharge. So silver plus will win, and Ag plus would in the end be the one that reduces to your silver solid. So in terms of observations, you can see that there will be deposits well, specifically grey deposits on the electrode. This is the observation that you have to note. So do take note that most of your observations come from the underlying reaction. So if you know the reaction, it's very easy to tell the observation. Next, your anode is where oxidation happens. Because you have a metal electrode, and we already said that copper is more preferentially oxidized, so it will be your copper that oxidizes to copper 2+ ions. And in terms of observations, you can see that the electrode will shrink in size, or it will decrease in mass. And you can also see, because copper 2+ is being added to the solution, your solution will turn blue as the reaction proceeds. Now, if I were to compare the voltmeter reading of this reaction over here to something like magnesium and copper as the electrodes, I would say the voltmeter reading here is lower because the difference in reactivity is lower between the two metals we're using, which is copper and silver. So there are very common questions in the exams that will ask you to compare the voltmeter readings, and you have to take note this important concept. The voltmeter reading, which measures the potential difference, is determined by the difference in reactivity. That's all for today's video. If you really learned something and you like this video, be sure to click on that like and that subscribe button so you don't miss out on free content like this. If you want to join my community of students at the Cambridge Institution, be sure to check out our link in the description below so that you can sign up for a free trial class today. Here you can learn the exact systems that we use at the Cambridge Institution to help our students improve in a short span of time and also achieve their grades of their dreams in the end.